In our last lecture, we dealt with the idea of making predictions about genetic traits based on monohybrid Punnett squares. In other words, we were crossing one trait at a time. You can imagine in real life, it's not like that. When two people have a child together, they cross 25,000 traits at a time, not one. Well, we're not going to cross 25,000 traits at a time here, but we are going to up it a little bit from 1 to 2, and thus we are going to do dihybrid Punnett squares. We're going to deal with two traits at the same time. As you look at our example here, we've got two traits listed. We've got eye color, represented by the letter E. The capital letter, being dominant, is going to represent brown eyes, and the lowercase e, being recessive, is going to represent blue. Now, a warning here, eye color really doesn't operate like this. Brown eyes are not dominant, blue eyes are not recessive. It just was an easy example to use, something that we can all relate to. The same can be said for our second trait here, hair color. We've got the capital H to represent the dominant, which I've made to be red hair, and the lowercase h representing recessive, which I've made purple hair. What's key here is down below. We've got the parents' genotypes. So what I have set up for this first parent here is that they are heterozygous for eye color. Therefore, brown eyes would be the phenotype. And also, heterozygous for hair color, thus would have red hair. So brown eyes, red hair in this individual. The other parent, parent number 2, is homozygous recessive for eye color. This person would have blue eyes. And they are heterozygous for hair color. So like the other parent, would also have red hair. This really now goes back to the third of Mendel's 3 principles, which we never really got around to talking about. We dealt with the principle of dominance and we dealt with the principle of segregation, but we kind of glossed over the idea of the principle of independent assortment. It's going to definitely come into play here. It's going to take a moment to get around to it, though. Let's look at this first parent. And I'm telling you, as we do the Punnett square, this first parent is going to be represented above. Now, you may have thought, hey, there's 4 letters and there's 4 blocks. Wouldn't we just write big E, big H, little h? That is definitely not the way to do it, even though every year when I explain this, somebody does it that way on a test. What has to happen here, and we need to look back at our parent down here, our parent number 1, is that you need to think about a dividing line existing between the E's and the H's. They really have nothing to do with each other. They are 2 separate traits. They just happen to be in the same parent. Remember, the outside of our boxes here really represents sex cells. Again, if we think of this as the father up top, these represent his different versions of sperm cells. Here's one sperm cell, here's a second, here's a third, and finally a fourth. All we're doing is representing all the different possible combinations of sex cells that this parent could potentially form. In other words, the big E could combine in a sex cell with the big H, and that's what's being represented here. The big E is just as likely, though, to end up with the little h, and that's what's being represented here. The little e could be with the big H, represented here, and the little e could be with the little h, represented here. 1/4 of his sperm cells should have that combination. 1/4 should have that, and 1/4 that, and 1/4 that. What I've just shown you there really is the principle of independent assortment. The big E doesn't necessarily go with the big H. It might go with the small. The little e doesn't necessarily go with the little h. It could go with the big. We've got to have all 4 possible combinations because when meiosis occurs, the genes sort themselves independently of one another. They have any number of possible combinations, and so we have to display each of the combinations. For parent number 2, it's a little more simplistic. Because parent number 2 is homozygous recessive for the first trait, for the eye color, and heterozygous for the second, the hair color, we don't end up needing all 16 blocks that you see here because parent number 2 doesn't have as many possible combinations of sex cells. They've got the big E that can go with the big H as represented here. They've got the little e that goes with the little h as represented here, and there aren't any other combinations. If you wanted to, you could write the little e with the big H again here, and the little e with the little h again here, and you could fill in all these blocks, and everything that you would do would still be correct, and you'd end up with the correct answer. You would have just done more work than you necessarily would have needed to. Once you have things set up with one parent here and one parent here, this becomes very simple. Just do exactly what you learned to do with the monohybrid Punnett squares. Bring together from the outside, down, and across, and recombine your E's and your H's together. So big E with small e, big H with small h, and you have one possibility of a child here that would have brown eyes and red hair. Do the same here and here and here, and you end up with all the possibilities of what this child could be. This is going to require some practice. That's what's going to come next.